Hey guys, welcome back to another lesson, and in this lesson we're going to be covering distance, displacement, and vectors. Now this is the very beginning of kinematics, and there will definitely be more lessons on kinematics in the future, but I felt this was the most foundational topic that we covered, and this is used very largely in forces, static equilibrium, things like that, which you'll learn later on. You don't have to worry about it now. But again, vectors are very, very important, so I recommend that you pay attention and you do your best to understand them. And of course, if you have any questions, feel free to contact me. So basically, there are two ways that we measure movement in physics. We have distance, which we're all pretty much used to. If I travel 5 miles to a store, the distance I've traveled is 5 miles. But now we have this new word called displacement. Displacement pretty much doesn't care about the journey that you took to get there, it only cares that you got there. And this is going to make a little bit more sense in the next example, but there is the motto that life's all about the journey, and that is 100% true for distance. Distance cares what journey you went on, the entire path that you went on. Displacement really doesn't. So I provided a couple examples to kind of help this click for you because I know I had trouble understanding it at first. So let's go ahead and get started. Distance versus displacement. Distance is the total length you travel. So if I walk in a square, a 5 by 5, and I start at this circle, let's pretend the circle and triangle are the same point. So I start at the circle, I go all the way around, I know that I've traveled 20 meters. Easy enough. Now let's go ahead and talk about our new word, displacement. Displacement is pretty much how far is the start, which is the circle, to the end, which was the triangle. So how far is this distance right here? So assuming it's the same point, I'm just not very artistically inclined, assuming it's the same point, the distance traveled between the start and end is 0. That's displacement. It's the measure between the start and the end. Let's go ahead and do another quick little example just to help you understand it a bit more. So distance, we're all used to it. Let's say I start at house A and I go to the high school for some reason. We're going to go ahead and we see that we travel 5 meters and then we travel 2 meters back. So distance is the total length traveled. So we go all the way around and we know we went 5 meters there, 2 meters back. Our distance is 7 meters. Easy enough. Now displacement is a little bit different. It only cares about the start and the end points. Let's pretend that these are in a straight line, by the way. So we went 5 meters there and 2 meters back on the same line. So displacement, we're going to go ahead at our start point, which is here, 0. And we know that we went forward 5 and we came back 2. So we stopped at 3. So displacement cares that we stopped at 3 and we started at 0. So it's going to be the final minus the initial, which in this case is 3 meters. So in the eyes of distance, we traveled 7 meters. But in the eyes of displacement, we only went 3. So this is going to make a little bit more sense later when I start getting into vectors and resultant vectors, which are pretty easy things, so don't even worry about it. Let's go ahead and talk about scalar and vectors. Scalar is basically a quantity that doesn't have a direction with it. Distance is an example of a scalar quantity. Notice for our distance, oh, my bad, this should actually be, displacement should be 3 meters, and then the direction that 3 meters was traveled in, so we know in this we went east, so it should be east. We'll cover this a little more later, but I just forgot to add that little tiny bit of information. Anyways, a scalar is a quantity with no direction. Distance is a scalar quantity. Notice how when we said 20 meters, it was just 20 meters in general. We didn't really care if it was north, south, east, west, etc. So an example of that is also just 14 miles an hour. Just generally 14 miles an hour. A vector quantity has a direction. Displacement is an example of a vector. So like we said up here, we go 3 meters, but which way was that 3 meters traveled? Well, with a displacement, we know that we went east. So we went 3 meters this way. So another example is you could be like 14 miles an hour going north. And then that way we know we're going north at 14 miles per hour. So let's go ahead and talk about resultant vectors for a second. So that means we're no longer worrying about distance, we're worrying about displacement. So what is a resultant vector exactly? A resultant vector basically occurs whenever you add, subtract, add or subtract vectors. So what's going to happen here is we go 5 meters east and 2 meters west. So we know that our displacement is 3 meters in total, 5 minus 2, and it ends up being east because we go 3 this way in total. 5 east, 2 back, 3 to the right total. So the resultant vector is the 3 meters east. This is our resultant vector. It's basically what occurs whenever you add or subtract your vectors. So we subtracted these ones, and this is what was left over. So when we go to add or subtract our vectors, or we want to combine them in some form, we look at if they're parallel, anti-parallel, right angles, etc. So for parallel vectors, meaning vectors going in the same direction, we're going to add them up. So you see we have a 2 meter vector going east, a 1 meter vector going east. We see that they're going in the same direction, east. So we're going to go ahead and add them. So it's just 3 meters east in total. Now, what's going to happen if they're anti-parallel or they're going different directions? So let's say I'm going 10 meters east, but then 5 meters west. Well, we're going to go ahead and subtract our two vectors, anti-parallel. This is an example of an anti-parallel. This is anti-parallel. So we're going to go ahead and subtract them so we know we went 5 meters. Now, how do we know which way we're supposed to be going? We take the direction of the larger vector. So we know that 10 meters is larger than 5 meters, so we're going to go ahead and take the direction of the east. So 5 meters east. That's where the east comes from, is the larger vector. Now, what's going to happen if we get a little more complicated with our vectors? Let's say we're going to go ahead and I want to know the resultant vector of going 3 meters to the right and 4 meters north. Well, that's where we're going to have to get into trigonometry. So we know that this is going to form a right angle, obviously. So that's 90 degrees. And we know that the Pythagorean theorem works for 90-degree triangles. So we're going to go ahead and do 3 squared plus 4 squared equals c squared. So then c is equal to 5. That means that this green arrow right here is 5 meters. Easy enough. So now, where on earth does east 53 north come from? What does that even mean? When you talk about vectors, remember that we need a direction associated with them. See how they all have east or west or something like that. So in order to get our resultant vector's direction, we have to find this angle right here, this little angle theta. And we're going to go ahead and show you how to do that in the vector practice problem up above. But basically, once you find the angle, you go right or left or whichever way you want to go. But you usually do your left, your right first, and then you put your angle and then up or down, which I'll show you in the next problem, so don't worry about it. So let's go ahead and do a practice problem. Very simple. Start at A. So we'll make a point A. Easy enough. This problem is basically solved already. So we're going to go ahead and write 3. All right. So we'll say 3 meters east. And then we're going to go ahead and go up 4. Okay, we're going to go up 4. 4 meters north. Notice how whenever you add and subtract your vectors, mainly when you add them, they meet tip. The tip of this vector meets the tail of that one. The tip of this vector meets the tail of that one. That is how you add and subtract your vectors. If you're subtracting vectors, it would be an example like this, but notice these ones even meet tip to tail because they're anti-parallel. But for right angle examples, they will always meet tip to tail like this. So whenever you go to add or subtract them, make sure you draw them going tip to tail, tip to tail. So we know that this is what we got from our drawing. So we went 3 meters right, 4 meters up. Now we want to find the displacement. Well, I thought we were talking about vectors. Remember, the displacement is a vector. So we're going to go ahead and find the total displacement that we traveled. We know that from earlier, displacement only cares about the start and the end. So we want this distance right here. Whoa, this looks just like a right triangle like we did before. We know that we have 90 degrees right here. And so we want to go ahead and find this distance. So we're going to do the Pythagorean theorem, obviously. 3 squared plus 4 squared equals c squared. We know that c is equal to 5. That's a perfect right triangle, okay? Pythagorean triple, I mean. So c is equal to 5. We know this is 5 meters. We need to now know what direction is this vector going in. We already know that it's 5 meters, but we need to know what direction it is because it is a vector, and displacement has direction, so do vectors. So pretty much, we're going to be solving for this angle right here. How do we find that angle? Well, we know that from SOHCAHTOA, if I draw that out real quick, I'll do it over here. So, oh, this is awkward to write. SOHCAHTOA. Alright, excuse that handwriting. SOHCAHTOA. So we have the opposite and the adjacent side of this angle. So we're going to be using tangent, right? So in order to find that angle, we're going to go ahead and do the inverse tangent of the opposite side, which was 4, over the adjacent side, which is 3. So the inverse tangent of 4/3 comes out to be, if you type it into your calculator, 4 over 3, around 53 degrees. So say this is around, say this is about 53 degrees. So how do we write that into here? Well, we know that we started going right, so I always like to put my left and my right first. You can do it the other way, but when you solve for it like this and your angle is over here, you always want to put your left or your right direction first. So our right direction is east, so we're going to go ahead and put east. How far up did we go? Well, we're at an angle of 53 degrees. This is 53 degrees, so we'll write 53, and then we know it goes north, so we'll put north. All right, that's that, easy enough. So east, 53 north. I'm going to make that green just so it looks a little nicer. So we know that we're going 5 meters east at 53 degrees. So the way for this to be read, is we're going 5 meters east. So we're going 5 meters east, and then we're switching direction and going 53 degrees north. So that you know that you're going east, and then you know that you're going north, and this has to be 53 degrees. Alright, I hope that was helpful. If you guys have any questions or comments, feel free to contact me at any time. I hope this helped you guys, and thank you so much for watching. See you next time.